Welcome students, we are back with another lesson. In this lesson, we'll discuss de Broglie waves. So what are de Broglie waves? The waves which are associated with material particles in motion are known as your de Broglie waves. They are also known as your matter waves, and the wavelength associated with this wave is known as your de Broglie wavelength. Now let us derive de Broglie wavelength, or we can also say we can derive the expression for the de Broglie wave equation. Consider your photon as an electromagnetic wave of frequency nu. Then its energy is given by the expression E equals to h nu, where h is your Planck's constant. Let this equation be your equation 1. Now consider your photon is having a mass small m. Then the energy associated with the mass m is given as E equals to mc square. Let us give this expression a number, equation 2. Here c is the speed of light, now look at your expression 1 and your expression 2. Both are these equations of energy. Therefore, from equation 1 and equation 2, I can equate the left hand side also, since both are the equation for intensity. Therefore, from equation 1 and equation 2, we get h mu equals to mc square. Now we know that your speed of light equals to the wavelength multiplied with your frequency. So from here I can write the expression for frequency as mu equals to, I'll send this wavelength to the other side, so c by lambda. So I can substitute this frequency here. So I can write, so after substituting this value here, I can write hc upon lambda equals to mc square. Fine. From here I can cancel this c and this square, or I can also write h by lambda equals to mc. Fine. Now what we will do, we will inverse it. I'll send this lambda to the numerator, this h will come to the denominator. Similarly here, this mc will come to the denominator. Then so I'll get lambda upon h equals to 1 upon mc. I can send this h here, I can cross multiply, then I'll get lambda equals to h upon mc. Now we know our momentum of a body is defined as the product of the mass times velocity. So this mc represents your momentum. Therefore I can write h upon p. Therefore lambda equals to h upon p. This is your de Broglie wave equation. Fine. Now why is this expression important? This expression is important because if you look carefully, here we have written energy. This energy represents the energy of a wave. If you have a wave, then its energy is E equals to h nu. And if you have a particle or you have any body, then its mass energy equivalence is E equals to mc square. So this one represents the energy for a wave and this one represents the energy for the particle. So using this two energy expression for your wave and your particle, we have derived the wavelength expression. Now why is this expression very important? This expression is important if you look this term wavelength. Wavelength is generally associated with your waves. Fine. Wavelength is associated with waves, whereas this P is your momentum. Momentum is associated with particles. Any particle will have a momentum. Therefore, this de Broglie wave equation gives us a relation between the wavelength and the particle. Therefore, this derivation shows us that when the particle is very small, okay, in the size of electrons or smaller than your electrons, okay, mind you the electron size is 10 to the power minus 15, okay, it's very small. So whenever a particle in very small dimensions, in that case what happens, the particle will exhibit the wave nature as well as your particle nature. This is what we have seen in your photoelectric effect. The photoelectric effect shows that your light behaves as a wave as well as particle, right? So you just remember this expression, right? So let's take an example on this wave equation, okay, on this expression. Let's take an example of an electron. So here let us derive the wavelength of an electron. We know that your electron is a particle. If it is a particle, that it must have a momentum, but what we'll do, we'll try to derive its wavelength of this electron. So consider you have a evacuated glass tube, okay, there is vacuum inside, fine. Now suppose you apply potential to this plate. Now whenever you apply a potential, what will happen, the electrons from this red plate, okay, the electrons from this red will be attracted towards this green plate. Why is it so? Because electrons, what is the charge of electrons? Negative. So negative particles are attracted towards the positive terminal. Can you see it is connected to the positive terminal of the battery? So the electrons will move in this direction. Now if the electrons moves in this direction, then electrons will undergo a motion. If electrons have a motion, then they will have some kinetic energy because of their motion, fine. So what we will do, we will try to derive the wavelength for the electrons which are emitted from this plate, fine. So consider an electron which has a mass small m, charge small e. The electrons are moving with a velocity small v under the influence of the potential difference capital V, fine. Now if this electron of mass me moving with a velocity v, okay, then what will be the kinetic energy due to its motion? The kinetic energy is given as half of mv square, fine. Now look here, mv square I can also write as half of mv multiplied by v. This term will give me v square, so I've just separated this v term, fine. Now look at this part. What is the term inside the bracket? It is mass times velocity, and we know what is mass times velocity. Mass times velocity is momentum. Therefore I can replace the mv with p, fine. Now similarly, if I divide and multiply with m here, like this, I can divide and multiply with m. So again I have mv, and what is mv? Product of mass times velocity, it is momentum. So I can write this one as momentum p. And what is p times p? It will be p square. Therefore this expression can be written as half of p square by m. Fine. So this is also the expression for your kinetic energy which is gained by the electron moving with a velocity small v, fine, where this p is the momentum of this electron. Now, why is this electron moving? Why is it moving from red plate to the green plate? This is because of the potential being applied. Okay, so from here you can conclude that the potential is doing some work which causes this electron to move from the red plate to the green plate. Therefore, the work done on the electron can be written as E, the charge multiplied with your potential difference V, which is EV. Now, so the kinetic energy gained by the electron should be equals to the work done on the electron by the electric field which is created by your potential difference. So this two expression should be equal. Therefore, I can write P square by twice of m equals to EV. From here, let's send this 2m to the other side. Fine. Now let's send this square to the other side, then this will become square root. So your momentum can be written as P equals to root over twice of m EV, where m is the mass of the electron, E is the charge of the electron, and V is the applied potential difference. Now we know from your de Broglie wave equation, your wavelength equals to h divided by P. So what will be the wavelength associated with the electron? I'll write in the next page. Lambda equals to h upon P. Substitute the value of P from here. So it will be h upon root over twice of MeV. Now here h is your Planck's constant, whose value is given as 6.626 times 10 to the power minus 34 joule second, where m is the mass of the electron and its expression in its constant, whose value is 9.1 times 10 to the power minus 31 kg. E is the charge of the electron, which is a constant, and its charge equals to 1.6 times 10 to the power minus 19 coulombs. Now let us substitute these values here. So write down lambda equals to, substitute the value of h, 6.626 times 10 to the power minus 34. Then write this square root and write 2. Then substitute the value of mass, 9.1 times 10 to the power minus 31 kg. Then you have E. E is the charge of the electron. Substitute this value here. Fine. Multiply with V. Now when you equate these values, okay, you can find the values using your calculator. So when you find this value, what you will get? Your wavelength lambda equals to 12.3 times 10 to the power minus 10 upon V. Now this 10 to the power minus 10 meter, okay, we can substitute as angstrom. So your wavelength expression can be written as 12.3 angstrom upon square root of V. So this is the wavelength of the electron, which is accelerated through a potential difference of V. Fine. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So again, thank you.